Okay, good morning. I'm Yan. I'm presenting a team project effort here. Mike, in his speech, mentioned that when we usually put in a new software component, the integration itself becomes a new project. So this is it. Why do we do that? I don't have the answer either. But what I will present is our effort to reduce the cost of integration and streamline the process itself. So this is a project collaboration with a few project institutions and partners, including Arizona State University, USGS, and Kent State University, where Eric Schuch is sitting there. He used to be our. So I'll have a lot of live demos, so I have to switch between the slides and the terminal frequently. I apologize if that interrupts you. This is the outline of the talk. I'll introduce our purpose first, then I'll basically introduce our approach to address the integration of CyberGIS software components, which has 3 steps: to select a component, to integrate it, and to test the scalability on cyber infrastructure. And I'll give a progress update by having some live demos to show you the release we are currently working on and the framework of integration, and also some of the cases that we actually already implemented on cyber infrastructure. Then we'll have Arizona State University team presenting a case study. That's the parallel pPySAL component in this toolkit. And we'll conclude. I was asked to go forward, so I'll just quickly go through some of the introductory slides. So why do we do this? If we look at the 6 main goals defined in our NSF CyberGIS proposal, this toolkit thing actually covers 3 of the goals. If you look at the second goal, that's very obvious. We are going to deliver a set of scalable geospatial software components. So this toolkit is a software toolbox as a deliverable for this goal. And if you look at the third goal, that's to achieve the capability of tackling large-scale geospatial scientific discoveries. And this toolkit serves as building blocks for doing that. The 5th goal basically is the coupling of the software, the geospatial capabilities with the advanced CyberGIS, cyber infrastructure resources. So with this toolkit, we provide a computational solution to that. In terms of the role of this toolkit in the CyberGIS software environment, we have the gateway as an interface to end users, meaning those users who are not technical, but they have their scientific problems to work on. They go to the gateway. They don't directly deal with the CyberGIS toolkit. The toolkit itself is deployed. Mostly you'll access it through services. You're not going to type command lines to execute a command. But this toolkit is deployed on cyber infrastructure, meaning our users are selected for this toolkit users. It's a very small subset of CyberGIS users who are usually developers, the owners of local computing resources like clusters. And we have this GSO middleware to bridge the end user community and the high-end users. The definition of a toolkit, I just got one from this, the 30-year NSF report. So it is what it says is that it is a deep approach that needs in-depth investment of technologies and effort to make the whole software work. It's not simply a coupling of software components together and just ship it. It has to go through a rigorous process that actually represents a few topics in integration, research, and development. These are the objectives. The first objective, of course, is to gather a collection and deliver this collection of software components into this toolkit. We'll demonstrate the first set of components later. The second, actually, I think it's quite important, and probably is the most time-consuming part, is the establishment of and the maintenance of the CyberGIS Toolkit integration process, this framework, so that in the future, as more components are added in, our approach can be scalable. So basically, and the third goal is to just test all of the software capabilities on cyber infrastructure. Usually, we have a lot of resources on the leading cyber infrastructure in the US. If a component passes all the tests on cyber infrastructure resources, usually it will be usable on local clusters, which has much smaller scales. And the final objective is to make it highly usable by the group of high-end users. So these are the goals. In one sentence, I would say the goal is to develop a scalable integration approach to integrating a set of scalable software solutions in geospatial world. And this is our approach in order to achieve those goals. The first is the software selection. I'll briefly go through that. And the second part is the ongoing work we're doing. I'll brief about some of the complexities and the holistic framework we have to address that. And for the third part is the scalability analysis. If you write your software on local desktop and run several cores, you'll see a lot of problems when you run that on supercomputers. So that's the important step to actually test both the scalability to problem size and to the number of processors we can have on advanced cyber infrastructure. So the open source strategy, we ask that each component, if you want to contribute to the toolkit, it has to be open sourced. The toolkit itself doesn't have an open source license yet, but that's upon discussion whether we should have a license on the toolkit. For the component selection, I'd like to just introduce an example. This is a pREST blaster contributed by Center of Excellence for Geospatial Information Science at USGS. The project itself originally was an internal project in USGS, but once we got into CyberGIS, we found that we actually have a lot of needs for rapid map reprojection tool. For example, in our viewshed analysis, we have to calculate the distance on DEM, digital elevation model, the rasters. If we use the DEM source from USGS, the national elevation data set, we cannot directly use it because the coordinate is lat long. We cannot use lat long for distance calculation. Another example is the tau DEM. It's a parallel computing solution to hydrological analysis. It's also based on DEM. And there's a lot of distance calculations there, and we cannot directly use the NED data set. So what to do? We can try use some sequential software. What we found is that if we use GDAL has it's an open source geospatial software. It has a reprojection tool. If we use that sequentially to actually reproject the 20 gigabytes of DEM, it'll take 5 hours. It's not that bad, but if you are going to reproject the whole 1/3 arc second 10-meter resolution NED data set, it's going to take forever because the data set size is about 0.5 terabyte. So we got into this project and we want to select the pREST blaster, and it's actually a mutual process. The selection itself actually made USGS think about the restructuring of the software. So this is the end result. So originally everything on the up part is a single box. Now USGS is separating them into 3. The library in the center actually stores both the parallel computing solution and the desktop solution, which is MapIMG. And the users are classified into 4 categories. and the left two parts are, three parts are actually the users of a CyberGIS Toolkit. So we actually made a significant progress last week. I think David Medley, the lead developer of PRES Blaster, got really excited about this restructuring, and he put a lot of effort in it. And we set our bar high to be just able to reproject the whole 500 gigabyte AED data set using this software. So that's coherent to the story Mike and Ling were talking about, to just map the whole thing instead of divide and conquer. Because in map projection, if you divide and conquer, you'll see a lot of gaps in each tiles. Well, the challenges, of course, there are a lot of challenges. Specifically, when we integrate a component into cyber infrastructure, we have extra challenges to deal with. Some of them are the challenges you can have when you develop desktop software. For example, programming language, if you use different programming languages, and application or library, they are different. Dependent libraries for any operating system on your desktop, it has to deal with those in order to install the package there. Code availability, in research world, we actually deal with a lot of research code. We have to go through a process to polish the code and make them a production quality. Programming models in parallel computing world, we have all sorts of parallel computing models to integrate, and each model has a bunch of different implementations as parallel computing libraries. And finally, the cyber infrastructure resources. Each supercomputer has its own strengths, so you have to be able to fully leverage its strengths. To do that, you have to cope with all the specific libraries, implementations, architectures, file system, storage system, CPU architecture to deal with those. And it is a multi-level integration, because the first level is desktop level. That we don't do it. We let developers handle that. Next, once it works on a desktop, you don't know if it works on other operating systems or different versions of libraries. We'll put it in our test framework to actually help you identify some of the library inconsistency issues, or portability issues, compatibility issues, and then we do scalability test on cyber infrastructure to make sure your solutions is scalable, so that if we give you 10,000 CPUs, you are able to use it. And software distribution is common for all kinds of integrated software, but that needs a lot of actually time and energy investment. The strategies, I'm not going to go through one by one. Those are quite familiar if you are a software developer. What's unique is the computational intensity analysis, which we'll actually address in the scalability test. Am I doing okay? Okay. So in terms of a multi-layer, we basically have 3 layers on the left, as I mentioned. The second layer, after we get the code from developer, unit test and function tests are done. We get the code, we throw that into a national middleware initiative build and test cluster, which sits in at the University of Wisconsin. That's nightly built. And anytime you change the code, we'll throw that into the test framework. Then scalability analysis enhancement, currently we're doing that case by case by working with each software component at a time. We foresee that we should actually leverage the experience we gained there and to streamline the process and develop corresponding modules, so that all three levels can be managed through a central continuous integration management service. With this box, we don't have yet. We are developing that. So I already went through this, so I'll quickly skip. Now it's demo time. I'd like to introduce the components first, then we'll illustrate the AMI testing case and the cyber infrastructure deployment part on the Exceed, which is NSF Advanced Cyber Infrastructure project. So what I'm going to do now is to switch to the browser. Yeah. So this is a page of the toolkit. I don't know if it's linked through the homepage. Probably not yet, because we just released this toolkit in early September to internal members and invited people to test. It has basically 4 components. Parallel pPySAL is a pPySAL project is being developed by Arizona State University. There are several pPySAL functions in it got parallelized and tested. We integrate that into this toolkit. P-Raster Blaster, I mentioned that. Parallel agent-based modeling, that's what Eric did when he was with us. It's an illustrative software to show how you should develop scalable agent-based modeling applications. Spatial text, it is a sequential program, but it's able to handle massive social media data in order to geocode the information. It's a Perl module. So you're welcome to come to this page to see the introductions and download the toolkit. You can download it separately or as a whole. We currently only provide a source package. The packaging system we are building eventually will produce binary packages for different flavors of Unix. Sorry, we don't provide Windows or Mac yet, but Mac is on the plan. Windows, I'm not sure. That's based on the criteria is based on what kind of operating system, cyber infrastructure, supercomputers use. So I'll just stop here and feel free to go to each component and let us know your feedback. That's the purpose of having this release here. We are in the initial phase of this project to shape up the toolkit layout, licenses, packaging mechanisms, release cycles. So we have a lot to do, but please give us your feedback. Now I'm switching to terminal. If you're a developer, this should be quite familiar. So right now, I'm on a supercomputer hosted at the San Diego Supercomputer Center. This supercomputer is called Trestles, which has 10,000 CPUs. We also developed the toolkit on other supercomputers, including Stampede at Texas Advanced Computer Center, which has 100,000 CPUs. So the software, we're dealing a lot of heterogeneities here. One heterogeneity is supercomputer itself. The second one is the software environment. This is a shared supercomputer. There are a lot of users that are using that right now. This is a command to show all the. Can you really see? Yeah. Okay. No problem. So these are the submitted jobs with computing jobs by different users. If I do a count, now we have over 4,000 jobs that are using this 10K CPUs. And the software environment, well, this is a list of a software environment. That may be a lot, but what I want to tell you about the message is that even for one software, it has multiple versions, because it's just the case that developers compiled the code that uses this version, and he doesn't want to switch to another version because of the development time is limited. So, and different version has different capabilities, not necessarily back compatible. So supercomputer administrators usually deploy several versions on for the same component. Well, there's a lot of and the compilers. You have GCC, you have Intel compilers, you have PGI compilers. For parallel computing, if you're familiar with MPI, it has, on this machine, it has only two flavors, OpenMPI and MVA-PH2, contributed by Ohio State University. So when you develop an application, you need to choose your compiler, MPI model, and the necessary tool, libraries like listed in here. Well, ours are here. So this is a process we are still establishing. Once we have the toolkit, we compile the toolkit based on each version of a compiler, MPI. We have to ask the administrators to actually set up this for us. But right now, it has a user mode set up so that we can actually incorporate the CyberGIS toolkit components into this centralized software module management system. So. For example, if I say this parallel ABM code, if I just type that, you cannot find it. This software environment supports the dynamic loading and unloading of software tools. If I do module load, PABM, now at least it tells me it needs some parameters. And it's already in the load path. So this is the way we see that we can provide this to the high-end users. If you are a cluster administrator, you deploy this toolkit, you put this software environment configuration into that, and for the developers, they only need to do the simple command load and unload. This is a way we see that's really useful for users. What I'm going to demo is the four components. Let me switch to another terminal. On this terminal, I already grabbed the 64 CPUs. And I'm going to just load CyberGIS PABM. I'm going to just run using MPI, using 4 cores, and tell it the machine file and just run it. This is where I go to find the. Oh, it doesn't wrap correctly. It doesn't affect it. It doesn't affect me. So it's running. It has a lot of input. So I redirecting that. It's a very simple case. If we look at the log, this is basically telling you it's setting up environment with 4 processors and their agent environment communications. And these are the iterations you run through to the end. So this is a PABM. It's illustrative because Eric told me each PABM application is specific. This is just to show you how to develop scalable solutions. Another thing I want to demo is to load spatial text. And I'm going to this directory. It has a sample data. It's basically some texts. If you give it Twitter data, it will geocode the Twitter data. If you give it newspaper, news media data, it will geocode all the addresses it can find. It is big. It has a big library of the mapping of the location and the text information. So if I say it's a Perl, so I have to do give it an input in sample sample and give it an output in, it's in CSV.
It's also running on trestles?
Yeah. Oop. This is output. So basically, it gives you a lat long information for all the address information you find. We found that it's really useful when we do this full mapper application that we'll demonstrate later. And now it is the PREST blaster. To go back. I have a test script I can show you. You just look at it here. I'm using 64 cores to reproject a data set. Let's illustrate it here. It's a DEM, it's a GeoTIFF, and then outputted to the output file. And the target projection is MOID. It'll take probably 10 seconds because it's really a small data set. But as I mentioned, David already made it work on 16 gigabyte DEM in 70 minutes. So let's look at the log. Yes, this is basically a GDAL output of the metadata of this DEM. And this is tells you the progress of each processor. And in the end, you'll see this timing information for each process. It takes 5 seconds for a very small data set because it needs a relatively expensive startup time for all the processors to be gathered together to work on this. And if I look at Toolkit, and parallel pPySAL component will be demoed by our ASU team. So, so far, any questions? Yeah.
So I'm interested in the spatial test. So what's the geocoding library or any get here behind the toolkit? Or when you do the query?
Okay. So for individual questions on the components, I'll defer that. If you have questions about this infrastructure and this terminal environment, I'll answer right now. But that's a good question, and basically I have to go and let's discuss that offline.
Yeah, sure.
Sorry to cut you off. Yep. Before I give the stage to Serge, let me just mention that we only integrate the 4 components, and the dependencies we're dealing with is illustrated in this diagram. So like a PAVM, it depends on a performance profiling library called IPM, which again depends on a low-level system library called PEPI, developed by the University of Tennessee. And it uses MPI. MPI is also used by PREST Blaster. Meanwhile, PREST Blaster also leverages the parallel file system capabilities for outputting the raster file, which is called Luster. And it uses a GDAL library to handle the metadata and file format stuff. And the GDAL, if you don't compile that with a projection software like GEOS and the ProJ4, you'll get error. So we have to handle all these. And spatial text is the most simple one. It only depends on Perl. For pPySAL part, I'll let Serge handle that. Okay, now I've give stage to Serge. Oops. I should put it here. And see.
And then you're going to come back for the...
Yeah.
Okay. All right, I just want to give you a little background on what parallel pPySAL is and how it fits into the larger project. And then Yan will be responsible for the actual demo. Okay, the motivation for this, I'll just jump ahead here. Yan, how do I get that one page? Thanks. Actually, Jay, Laura, and I are working on this component, but we're dependent on the efforts of a large number of people, many of whom are in the room, who've worked on pPySAL throughout the years. And Luke's going to be talking more about pPySAL later, so I'll let him speak to some of the organizational aspects since this is the middle of the demo. The original motivation was to leverage some tools that we have been building at different institutions for several decades, GeodaSpace, or Geoda and STARS, and then put the common data structures and algorithms into a library that we could then rebuild our own specialized applications on, but more importantly, make it available to a wider community. And this is prior to the project that we're engaged in now. The goal is to enable pPySAL to be delivered in a variety of frameworks, and we're going to see examples of this here today with the toolkits, but we're also working with our partner Esri to develop toolkits for Esri, working with QGIS folks, as well as rebuilding applications that are rich GUI clients and folks who want to work at the shell. It's there as well. There's several main components to the library. You'll see demos of some of these today. I'm going to focus on a piece of the ESDA library in this talk, namely map classification, choropleth map classification. Luke will be talking about spatial econometrics, and then Wen will be talking about some of the work on metadata and provenance for spatial weights. So where does the pPySAL project fit into the overarching goals of the larger project? This part is addressing the fifth question. If any of us who've worked with software either as developers or users in spatial analysis, you're aware that it's been written in a single CPU frame of mind, right? So when we developed the initial versions of the code that was in pPySAL now, we didn't envision the rich opportunities we're going to have to engage with HPC environments. So that brings up the question of how do we need to revisit the design of that software to tap into the potential to scale up to large problems that Mike talked about this morning. And that's really what the pPySAL project is focusing on. So we call it pPySAL because we need yet one more P. It's PySAL because it's written in Python, so that's the primal P there. The goal of the pPySAL project, I think the most important part is the last bullet, and this is something that I've heard several times now. Last year at GI Science, Buddha made this point that we really don't have a good roadmap for folks who are facing this challenge of how to map different spatial analytical problems and techniques into what the CS literature would tell us are parallelization strategies. So I heard that last year. I rewatched some of the keynotes from this conference last year. I was in here, unfortunately. Mark Cahegan made the same exact point. We need this roadmap, so that's basically 2 years. We don't yet have the roadmap. So we want to try to contribute to filling in pieces of this taxonomy by using what we have in pPySAL as a point of departure. And the approach is to look at the different types of parallelization that are well known in CS literatures and map them to different spatial analytical problems. Okay, so that's step one. And then specific to pPySAL, since it's the code that we actually have built and have and know painfully well, what are the different opportunities within the Python environment for parallelization libraries, and how can we map them back to this taxonomy that's more generic? And we like having pPySAL to work on because it does have a fairly broad coverage of the spatial analytical research stack. There is obviously previous work done on applying parallelization strategies for particular spatial problems, but they tend to be focused on that particular spatial problems, and the extent to which we can learn for those and map those lessons to other types of spatial problems is something I think we don't have a lot of stuff to go on yet. So the existing work we've done on the team and the team is the broader team with our colleagues at Urbana, is to look at parallel local Moran implementations on trestles. That was the initial start. It was fairly simple because it's embarrassingly parallel. You're using permutations, and the code can be farmed out fairly nicely there. The more challenging ones that we're dealing with now have to do with topic that came out this morning, partitioning, regionalization problems. So we have a max-P algorithm in pPySAL. Wenwen's worked on a P-compact regions problem with Mike and Rick Church. And to implement those in a parallel approach is much more daunting, because you're not just looking at farming out individual data streams to different cores. You actually have to have inter-core communications, and that's a much more challenging problem. And we're spending quite a bit of time trying to get the parallel version of the max-P algorithms to run satisfactorily. In the spatial econometrics library, we've used parallel modules in Python to deal with spatial regimes. So when you have different model specifications, if you will, or different parameter values for subsets of your data, we can parallelize that in the SP-Reg. And then today, what we're going to do is build on some earlier work with Luke and Rob Polly and some other colleagues at ASU, where we had an initial foray into this question of there's an embarrassment of riches in Python for parallel libraries for different architectures, SMP architectures, distributed architectures, and it's sort of a challenge to get your head around, well, which one do we want to use for our problem? So we picked one simple, relatively simple problem, that is Fisher-Jenks optimal map classification, and use that as a test case to take the serial code from pPySAL and implement it on these 3 different libraries and then compare them. So that was our initial approach, but then we wanted to revisit it so everyone's familiar with map classification. All right, it's a partitioning problem, but a simpler one because we have 1 dimension, not 2-dimensional space. So we want to identify K classes that partition the data. Many different ways to do that. The Fisher-Jenks formulation is an optimal classifier, so it has complexity of n to the k. And to get our heads around how it works, it's a good exercise to do by hand for a very small case, because it looks like a complicated algorithm, and it turns out it actually is, although there's a lot of folklore about how it's implemented in our world. Basically, you need to compute a diameter matrix. So this is going to be an n by n matrix, so we have n squared memory requirement. And all that is, the first row tells us what's the total variation for a cluster or class that would form from the first observation out to the nth observation or the 10th observation. Okay. Second row tells us the diameter matrix of classes that would start with the second observation, go to the nth observation, and so on. So that's our diameter matrix. We need that. The second matrix we need is called the error matrix. Okay, and what this does is it tells us this is going to be k by n in memory, so not that expensive in terms of its footprint, but calculating it, there's a compute cost. And what the values in the error matrix tell us are the value of your objective function for the optimal partitioning. Let's say row 2 is for a 2 partition of the data, beginning with the first observation out to, say, the 10th observation or the 100th observation. And then the third row does the same thing, but for optimal partitions into 3 out to the column. Okay, and that is more challenging to compute. There's more intensity there, more compute intensity. Okay, so there's 4 steps to the algorithm. First step is calculate the diameter matrix. Then we're going to calculate the error matrix sequentially by row, and that's an important point to keep in mind. Then once we've built the error matrix, you do basically an exhaustive search for finding the optimal partitions for a user-specified k. So the user is going to tell us how many classes we want. And then once we have that information, we can basically roll back from the error matrix to recover the actual composition of the cut points. What are the class boundaries going to be for the classes? So the initial implementation, the parallel implementation of that algorithm from pPySAL was to focus on the simplest part, parallelizing the diameter matrix. Right? That you can do that in parallel for each row, or if you want to load balance it, since we're only concerned with the upper triangle of the matrix, you can do it that way. So each cell in the matrix, that's the formula we need to deal with. What we've done since then in this work that we're reporting on today, the work that's in the library, is to use, number 1, shared memory so that the different cores can write to fill in the diameter matrix, but more importantly, also the error matrix. In the original implementation, we didn't deal with the error matrix from a parallel perspective. And then vectorizing the code. We actually hadn't done that in the first version. Okay, so just to give you some ideas, this is on a SMP machine, similar to what we saw in the earlier talk. This is the original serial code. So this is a problem where you have n polygons. So we want to do a choropleth map. And these are the runtimes for different levels of classes, so 9 to 5 classes. So right away, you see that this is fairly expensive to do for even a modest-sized problem in serial. But once we move to the parallel version, we can expand the problem and deal with larger problems. And more importantly, the runtimes are much, much faster for smaller and larger problems. So we're getting speed up curves on the order of, in the best case, say in the 8,000, which was the maximum problem size for our serial implementation, we're pushing up to 1,000 factor for the speed up time. Now where does that come from? A lot of it comes from vectorization of the code. That's a big speed gain there, but also then the parallelization itself. On a factor of about roughly 3 of the overall speed up is due to the parallelization. Okay, so the lessons learned before this gets demoed in the environment that Jan has built is that vectorization for us might be fast enough for small problems because that's where we get a lot of bang for the buck. But a broader lesson is that it is expensive to implement this stuff. So since human capital is rare in our field, we need this taxonomy to tell us where should we focus our efforts in terms of this porting of these single sequential algorithms in spatial analysis to problems that have high demand and are important. That's probably where we should be focusing our energy. Okay, so we're going to do some more work, but the thing I want to leave with is the idea of general portability. pPySAL is basically research code because it's helping us with this project, but we're at a stage where we're just about able to push some of this back into regular PySAL, but then for this project move it into the toolkit that Ian and colleagues have built. Thank you, Serge.
So let me go back to the terminal. It's a quick demo of the Fisher-Jenks algorithm in pPySAL. What I will show you is the script. Here I'm going to use a different number for cores, up to 64. And with 5 classes, and the data set size is 10,000. If I run that right now, it should fail because it could not find it. So if I load CyberGIS pPySAL, there are 6 cases, so it'll take less than a minute to finish. While it's running, let me switch back to the slides for the conclusion part. Sorry. So we have built this toolkit, and we released the alpha version for comment, and we urge you to go there and have a look. If you're not a developer, please ask your developers to help us to evaluate the process and see. Mostly you need a lot of dependent libraries to work with. That's something we're still working on to set up a virtual box that has everything inside so that developers can test it. But we welcome feedbacks, and we really need your suggestions and advice. I hope that's a good overlapping of the computing time. So as you can see, if I just use 1 core, it's finished in 23 seconds. If I use 32 cores, it's finished in 2.5 seconds. If I use 64 cores, it's taking the same amount of time because this node only has 32 cores. So that's the physical limit. By doing that, I think I'm done with the presentation, and we can switch to the gateway part of the presentation. Because if you're dazzled by these command line things, it's okay. You're not going to do this by yourself. You are going to access the gateway, which is much easier environment that's familiar with. You are familiar with. Okay.
Questions for Jan? Let's thank Jan first. Questions for Jan also? Yes.
So it's good to see that these are working fine. That's but what might be useful to also look at what went behind the scene, as you try to scale this, what was the difficulty and how easy it was, or no, that kind of question. How did you do the scalability analysis?
Yes.
The program that was running sequentially, how did you prioritize that? So those are the things that might provide some insight.
Yeah. We currently did 3 to 4 cases on the software components. What we so far identified are mostly the coding problem, which didn't consider the possibility of using a larger number of processors. They tested it on the local cluster, the local shared file system. It worked okay. But when you scale that up, the divide and conquer, the partitioning mechanism could have problem. And the data I/O is another big issue. When you have 10 processors writing to the same file, that's fine. If you have 10K processes writing to the same file, that has serious issues that we have to deal with by profiling that using some data-aware profiling tools. And also the load balancing issue is one where we identified. But there are more where we can